So what the intermediate value theorem basically states is that, let's say we have a function and we're gonna just choose, we're just gonna graph it. So we're gonna have our x-axis and we're gonna have our f of x-axis, and let's say we just choose points A and points B, and point A, let's make it a little lower. So we'll make this guy a little lower. So let's say we chose f of A and f of B, right? So these points will just correspond with each other. So A will go to f of A, B will go to f of B. So basically they're saying, like, you know, if we choose a output value between f of A and f of B, so we can choose any value. Maybe I'll choose something here. Alright, I'll choose like this guy. Okay, so they're saying if I choose that guy, is there going to be a value here that corresponds to that guy? The answer is yes, because if we draw a line, and we're also going to always, the theorem says only if f of x is continuous. So this is a continuous function. So the idea is that can we draw from this point to this point without passing that line? And the answer is that we have to pass that line. So we pass the line, you see? And see, the point at which we pass that line is going to be in between A and B. And just to put it in formal words, basically what it's going to say, you know, if we have f of c, right? F of c is something like this. F of c. If it is between f of A and in between f of B, then, you know, C, the point C, for example, this is C, then the point C also has to be in between A and also has to be in between B. Now let's see applications of this theorem. So this theorem is useful when we want to prove that a function has roots between a certain interval. So if we graph the function again, and let's say they gave us an interval like 1 and 5, right? And let's say that f of 1 will give us a function value of like 5, and the f of 5 will give us a function value of like negative 5. So the question is asking, using the intermediate value theorem. By the way, intermediate value just means, this basically just translates to like between, right? Between values, right? So between these values, that's how the theorem name comes. And so they're basically, we're going to prove that this kind of function will have roots. Roots meaning when we plug in an x value, the output will be 0. So on the x-axis, right, when we plug in 1, we get 5. And when we plug in 5, we get negative 5. So if this is a continuous function, at some point it has to cross the x-axis. And just like that, we proved that this function has roots. Now let's look at some example problems that I encountered. So let's say we have a function f of x equals 2x squared. The question is minus 5x minus 1. Okay, so we just have a function. And they said, suppose, wait, what does it say? It says, okay, let's suppose that f of c is negative 2. Okay, does that mean that c is in between 0 and 2? So it's not, we have to kind of translate this into a way that we can use the theorem. So whenever I see these kind of questions, I just like to draw a graph, because then I'm like more confident that I'm doing this question correctly. So we have f of c is equal to 2, negative 2. So they gave us in intervals. So if we graph the function, we will always just graph the intervals they gave us. So we get 0 and 2. So we're going to see what happens when we plug into the function f of 0 and f of 2. So f of 0 is just negative 1. F of 2, that's going to be 8 minus, well, this is 8 minus 10 minus 1, which is negative 3. So negative 3. So you see f of 0 is negative 1. 0 is negative 1. Oh, this is a little too high and low for negative 1. Negative 1 is about here. So we will graph this guy. And we'll see that 2 is negative 3. 2 will go to negative 3. And the question asks, okay, f of c is negative 2. So we have f of c, and this is negative 2. So does c have to be between 0 and 2? The answer is of course, because let's say we drew a line for negative 2. If this function is continuous, it has to pass that line. And when it passes that line, we've assigned a value between 0 and 2, which means yes, by the intermediate value theorem. Let's see a very tricky example. Let's look at a function that is not continuous. So remember, we can always use the 3-step continuous test, but I want to look at this example. G of x is equal to 12 over x minus 4, and if we graph this, right? First thing we have to notice is that when we set the denominator to 0, we can see that 4 will not be defined on the graph. There will never be a value for 4, because we can never input the value of 4. So let's just look what the question is asking, and then it will make more sense. So the question says something like this. It'll say, you know, if g of c, so any value for g, is equal to 0, does that mean that 2 is going to be, does that mean this c is going to be less than 2, greater than 2 or less than c, less than 6? And so let's analyze this. So we're going to first always just graph the intervals they gave us. So we're going to see 2 and 6. Let's graph the intervals they gave us. So g of 2 and g of 6. G of 2 will give us, this will give us minus 6. G of 6 will give us 6. So g of 2, when we graph that, we will see negative 6 is right here. And we will see g of 6 is 6. Okay, we just, basically we're always going to want to graph the intervals they gave us. They gave us the interval 2 and 6. So we're going to graph these, the bounds, okay? The bounds, because this is the only guys we're working with. So let's plot it. So 2 will correspond to negative 6. 6 will correspond to 6. Okay? And they're going to say, okay, let's say we have a value g of c. We have this guy, g of c. Basically, we can draw a line. Let's use different color. Let's see, we have a line g of c, basically the x-axis. So, does this have to be true? So does our c value have to lie in between here? Well, what did we say about the value 4? The function is never going to go through 4. So if we realize that between the interval they gave us, there is a value at which the function is not continuous, we have to do more analysis, because this is not, we're not sure if this is just going to be a simple continuous function, because it's not defined at 4. It's not defined here. This is not an existing point. And so this theorem doesn't really hold true anymore. So so we're going to see what happens when we plug in something like 3. Does the function even have to go this way? And it turns out, after we do some analysis, we plug in more closer points like 3 and 5, we'll just realize that this function actually looks like that. It has 2 asymptotes. And so the question is, the answer is no, not continuous. So those are some applications of the intermediate value theorem.